And thank you, Julia and Jessica, for all the preparation work to make this all happen. And I'm really happy to see you all here today. I would say that my grandparents were far from the first generation to be aware of the particle, the relationship between particles and health. From Hippocrates, when his warnings to physicians to make sure they check with their patients and understand the water they drink, the air they breathe, the work they do, to Pliny the Elder, who talks about the diseases of slaves, which means the hard work, right? To the 800-year-old edict in London that forbids burning coal when Parliament's in session. That's really 800 years old. To the horrendous London smog episode that happened a mere 55 years ago, in which thousands of people died. And to our ongoing, to this day, issues between household air pollution and the burning of biomass indoors, and the air pollution related to that, and the air pollution related to traffic exposures, which in some cities in the world is getting much worse. Those of us in California are a little bit insulated. Through all of these, humankind has recognized that there is this relationship between the something in the air, as John said, that is doing something to us and our health. What I want to do is to start talking first about how, in a more 20th and 21st century world, we might examine that more quantitatively through epidemiologic studies and the role of exposures within them. So if we could imagine a truth in the world that we understand, in which there is some exposure that leads to, say, 10 cases of disease per 1,000 people, and there's a background rate of perhaps 2, we could have an exposed versus unexposed, we would have, of course, a relative risk of 5, right? Now imagine a misclassification of that exposure. So those people who were exposed carry their disease risk over in, they're truly exposed, they have a disease risk, but they're misclassified as unexposed, and they carry that disease risk with them, all right? And so we can imagine a 10% or perhaps 20%, so that what would happen then is that the number of cases of the disease group would go down, and the number of cases in the unexposed or classified as unexposed group would go up. So that then would lead to a relative risk of 2. I mean, a huge reduction. And one of the things I feel that is missing often as we look at various epidemiologic studies is recognizing this truth. It's an underlying difficulty in actually finding the risk that actually is there. We don't have perfect information about exposure, so even as we do the Bradford Hill criteria so we don't have false positives, we need to think about the limitations of our studies by related to how good our exposure assessment is and what degree of misclassification. Clearly the point estimate goes down, and so then it, with any kind of confidence interval, and by the way, the confidence intervals, I've never seen a confidence interval that's calculated taking into account the misclassification of exposure, that uncertainty. I would love to see that worked out. But in any event, we can clearly have a large effect, look like a much smaller effect, and furthermore go from significant to non-significant within the 95% confidence interval. As an example of how we can, this happens in our worlds of these multiple worlds of our various exposures to particles, let's look at some of the secondhand smoke data that we have. This is coming out of Ann Haynes, and this is actually using cotinine data and based on nicotine, which is a gas, but there's a particle relationship. So this is the distribution of the cotinine values in those people who report they have no secondhand smoke exposure, and this is the distribution among those who say they are exposed at home or at work. And that, again, still doesn't count the exposures in other places such as bars and restaurants. And again, Californians, the whole world is not like California, and there are many places you can still be exposed to those. So here, what we have is a very large overlap. This area represents the overlap between the two, and clearly we can have misclassification of exposed people as unexposed and unexposed people as exposed. So as an example of how this can impact a study, I like to cite some very interesting work done by Wincup et al., where in the, about 15 years ago, they decided to go back to stored blood and analyze it for cotinine to understand the exposures that people have. The blood was collected in the late 1970s, and now it's being analyzed 20-some years later to say what was their secondhand smoke exposure. Lots of problems with that exposure assessment, but it is a personal exposure assessment. And when they did that, and they used that value, and they looked at coronary heart disease and stroke, in the next 4 years from the time of the collection of the sample, they actually saw a much higher relative risk from passive smoking, over 3.7, that has normally been reported. A much higher risk. And it's comparable to that of light smokers, those who smoke 1 to 5 cigarettes a day. So this was a rather profound finding, in my view. And so then if we look, they looked again at the risk as you went out the years. And so if you looked 5 to 9 years, 10 to 14, and 15 to 20, we see a decreasing risk. Part of it may be that some of the people have had their heart attacks or whatever, but part of it may well be that there's been a change in exposure. During this 20 years that this is going on, there's been a decrease in the overall smoking rate, which leads to a decrease in secondhand smoke exposure. There have been more rules restricting smoking in various public places. And so I would maintain that the cotinine measurement made from a late 1970s blood sample becomes a less and less good estimate of the exposure, and then leads to a decrease in the apparent relative risk. So just to say, since this is the focus of the study, that we are talking about secondhand smoke itself, by itself, is a major cause of heart disease, of cardiovascular disease in the U.S. The California EPA has estimated 3,600 deaths, this was about 10 years ago, in California every year from secondhand smoke exposure, and in the U.S. 46,000. The European Union has an even greater estimate of risk, with 32,000 ischemic heart disease and 26,000 strokes deaths, again annually in the European Union of 2002. Now these are surprising results because we think of secondhand smoke as being much smaller. If you look at the cotinine levels, it's 1% in secondhand smoke exposed people than to active smokers. And the particle level exposure is about 1%. So this is really kind of quite a striking result. But there are some reasons to look at this, and I want to use these as, although that's secondhand smoke data, I'm going to use that. I want you to bear in mind these ideas because we're looking at cardiovascular disease, and everything may not be a simple linear function. So one reason is the endothelial damage related to secondhand smoke. Even a brief exposure can increase the number of endothelial cellular debris in the blood, increases oxidative stress and endothelial damage, all of which is important in terms of developing arteriosclerotic plaque. Another way to look at this is the endothelial function of the coronary flow velocity reserve. If we look at non-smokers, they have a higher level than smokers, and that is statistically significant difference in that. It's one of the things that might be contributing to smokers' increased risk of secondhand smoke. But if there's a 30-minute secondhand smoke exposure, we see that the non-smokers actually have a decrease, a significant decrease in that coronary flow velocity reserve, which then brings them to the same level as a smoker gets by smoking a cigarette, to the point that there's no significant difference between the smoker and the non-smoker from a mere 30-minute exposure. Okay. Second, in a study that John and I were part of, and I don't know if Suzanne's here, but several of us were part of, looking at acute vascular injury and the mobilization of dysfunctional endothelial progenitor cells, a mere 30-minute exposure led to profound changes in the vascular biology over the next 24 hours. An increase in the EPC numbers, but it turns out these were not great cells. They were impaired. They were not able to really function to repair vascular injury. There was also an increase in endothelial microparticles and a decrease in the flow-mediated dilation of the bronchial artery. All of that after a 30-minute exposure at levels of secondhand smoke that are typical of those found in bars. So the effect can be disproportionate. I would suggest that this could be true of other particles as well. Now, we talk about a dose response. We often look for a dose response, and we see that in smoking with lung cancer. What's very interesting, the more you smoke, the more packs a day, the steeper the increase in lung cancer. But we have an increase, but it's a small increase in heart disease. There's still more people who die from heart disease because it's a more common disease, but the relative risk increases more slowly and is not nearly as steep a function. If we look at that specifically, looking at smoking and ischemic heart disease, if we look from 5 cigarettes a day up to over a pack and a half, we have a much less steep line from a relative risk of 1.5 to 2. And we can look at, this actually is a function of age. So this is a light smoker, this is a heavier smoker, and they do have increased risks, but not as much as we might have expected. And that difference actually decreases as the person gets older. Now the question becomes, where does secondhand smoke fall in this category? Again, the particle exposure is maybe 1/100th that of a pack-a-day smoker. So we could imagine curves like this or curves like this. What we in fact see is, if we look at 65-year-olds, is that yes, they have a less of an impact, but a lot closer than we might have expected. And so this is important. And the secondhand smoke point on the curve is here. So we have a very steep curve from no exposure to mainstream smoke or secondhand smoke, active or passive smoking, even to passive smoking. And then it somewhat doesn't level out, but it increases much more slowly. So when we start looking for these dose responses, we have to be careful and realize not everything is a linear function. The hypothesis is that there are multiple causes. There are multiple ways in which particles can cause cardiovascular disease. And so some might be, say, up to this point at one level and affect everyone, and then another mechanism kicking in later. So perhaps platelet aggregation, which has a maximal effect at low doses, and then and this might be relevant to some of our environmental exposures, and then cause and effect mechanisms other than that occurring at the higher level. So again, there's a large number of deaths in the US and in the European Union and around the world that can be attributed to active and or passive smoking. So next I'd like to turn to some of the characteristics of particles that are important and looking at particle size. So, why does this matter? Well, we actually talk about 3 categories of exposure. One is the inhalable, which are particles that can be taken in through the nose or the mouth, and they come down to the larynx. All right, that's the what's called the HEV region, for those of you who've looked at that, and that is one size of particles can make it there. It turns out though that but to get down into the bronchial region, the tracheobronchial region, there's another selection that goes on. And finally, to make it into the gas exchange region, the alveolar region, the unciliated region, the particles have to be smaller yet. And so we can talk about these as this is the size distribution of the particles. So we hear a lot about PM 2.5, which I think is very important, but we have to be very careful about it. It's not the only thing that's important for health. And in fact, if you inhale a particle that has a lot of toxicity, here we are, in this region, it turns out even particles that have an aerodynamic diameter of 50 micrometers, 50% of those particles will make it into the head region. So, and if they are toxic, if for instance, if it's lead, or if it's a pesticide that's toxic, or some other toxic material that is a systemic toxin, then it is a serious problem. The whole concept of respirable particles and what makes it into the alveolar region really came about maybe about 100 years ago, maybe a little bit less, in examining silicosis and silica. And when people realized it wasn't the total silica dust that mattered, but that which could make it into the alveolar. And that's because silica actually affects the alveolus. So it depends on how the mechanism of what the toxin is doing. If it's attacking the alveolus in that region, then PM 2.5 might be more important, or respirable particles more specifically. But on the other hand, if it's intrinsically toxic, we might be more interested in the thoracic or the inhalable fraction. And the American Conference of Governmental Industrial Hygienists has been recognizing that, and they now are moving to have inhalable specific, thoracic specific, and respirable specific threshold limit values as their suggestions based on that information. So now the terms I've just been using are the terms that are used in the occupational world. The environmental world has developed separately, and you see the terms PM10 and PM 2.5. Now those are very sharp cuts. The cuts for respirable, thoracic, and inhalable are based on the theoretical basis and experimental data that tell us how particles deposit. So it's not a sharp cut in the body. It's that as the particle gets smaller and smaller, a larger percentage can pass through the various barriers that it has to go through in the body. However, in the regulatory world, PM10 was the original standard that was set in the 1990s, and that was based on trying to approximate the thoracic dose, and it's a reasonable approximation. To say PM10 is to say particles less than 10 microns in diameter are passing into the body. The PM 2.5 standard is often used and equated to the respirable. It's not really the same. As you can see, there's a significant number of particles out here that would be excluded in a PM 2.5, and these are particles that can make it to the alveolar region. But EPA was trying not actually to set something to be like the respirable particles. When they set that standard, they were trying to set a standard that would encompass combustion products. Now, those of us in the field all know that if you were going to do that, all the combustion products tend to be, the vast majority, under 1 micron in diameter. So you'd do PM1. However, there were no techniques, good, reliable techniques available at the time to measure that. And so they did PM 2.5. So we have that sense that that's what's out there. But if we could redo it, we might do it differently today. But that's what's out there, and that's what we're working with. It is roughly like respirable, which is what we're really trying to get at, but it is not identical to that. Again, intended to be getting at combustion products. which moves us to the ultrafines and nanoparticles. These are particles that are less than 1/10 of a micron in diameter. And these, just to know the nature of these, is that because they're small and there are lots of them, they tend to coagulate and accumulate rather rapidly to larger sizes. So right near where the combustion happens, you have a lot of these ultrafine particles, but as you move away from those areas, you have fewer. The classic example is along the freeway. Right near the freeway, very high levels of ultrafine particles, less than 0.1 micron in diameter, aerodynamic diameter. But very quickly, by the time you move just a few hundred meters away, the concentration drops dramatically due to this coagulation and accumulation. The other thing is that they're very important, and you're going to hear a lot more about these later in the day, but they're very important in the theory is there's a translocation. We've seen this in animals where ultrafine particles can actually travel from the nose through the nerve passageways into the brain. And so there is a sense that we can actually get doses of these ultrafine particles going to the brain, passing through the alveoli into the bloodstream, and so they can translocate from where they would otherwise go. They are heavily implicated in inflammation as one of the causes of inflammation, which I'm sure you'll hear a lot more about shortly. And one of the reasons they're thought to be particularly toxic is they have a very high surface area for the same mass concentration. So if one imagines an air concentration of 10 micrograms per cubic meter, that's the mass concentration. If all the particles were 2 microns in diameter, there would be, in fact, 2 particles per milliliter of air, and the surface area would be, say, 30 square micrometers per milliliter. But as you can see, if you move to smaller particles, 0.5, we have a lot more particles with a lot more surface area. And if we go to 0.02, even more particles. I mean, now we're getting to millions of particles, and the surface area it has increased quite dramatically. And fundamentally, this goes as a square of the diameter. So on the surface can actually be deposited toxic materials that are in the gas phase during combustion. So there's a lot of feeling, and also they're more available, biologically available. They're right there in the surface. They don't have to go through the material. So, okay. I think I basically covered most of this. There's this high spatial variability on these. So I'm just going to turn very briefly to talk about what the implications of all of this. And if we look at, in an environmental world, looking at, in Fresno, we've been doing research there for 17 years. And if we look at the distribution of particles in Fresno, it depends on the particle size. So first on the left here, well, I have PM2.5, and that tends to be more evenly distributed, whereas you can see the PM10 particles have a heavier gradient. And the coarse particles are the particles that are between 2.5 and 10. So PM10 encompasses both fine and coarse particles. So the distribution of particles heavily depends on the size of the particles and that spatial variability. Another place we've looked at that has been occupationally at the NUMMI plant, which currently now is the Tesla plant, where we have been asked to come in and do a study. There was concern about respiratory hazards, and we did a study and established that in fact in the welding area there were some respiratory problems, and in fact made some recommendations, and then we were asked to come back and evaluate the efficacy of the changes that have been made. So in doing that, we actually wanted to map the particle concentrations, and we used a variety of equipment, which included sampling with gravimetric sampling with a cassette. You weighed the filter before and after, and then a few direct reading equipment, some of which did PM2.5, some PM10. The GRIM spectrometer, which actually measured particle sizes from 0.5 to 20 microns in 15 different size bins. And the P-track, which it's not exactly ultrafine, it does less than 1 micron. So it includes ultrafine, which do not show up. People are often not aware that most of the ways in which you have a device that measures PM10 or PM2.5 direct reading equipment, usually because of the physics of how it works, it is blind to particles less than about 0.5 microns in diameter. So one needs to be aware of that you're not actually seeing those particles, and that's why we brought that along. So this is a map of the facility. It's quite large, and this represents many, many days of sampling with the sampling cart. This is the work that Dr. Saliu did as part of her PhD dissertation. And so this is respirable particles, and one can see quite a gradation in those particles. This is using particularly the Casella microdust. If we look at the submicron particles, this is from 0.014 to 1 micron in diameter. We see it's related but a different distribution. So depending on what you're interested in, what you think is important for the health effects you're studying, you would find different patterns, and you need to look at that. And this is just a table that summarizes some of that. This is from the GRIM data where it's sized into these different proportions. And you can see that as the size gets larger, the number of particles goes down. And the P-track, of course, sees far, far more particles. That's quite typical that you see something like that in doing this. So in doing this work, Arden Pope kind of pointed out at one point, he's done a lot of work looking at cardiovascular disease and particles in the environment. He pointed out that we're in this situation where we have information about cardiovascular disease and smoking, and that's on the right here, in increasing numbers of cigarettes, and looking at cardiovascular disease and secondhand smoke, which is whatever color we call this. It's a dirty brown. It looks like, okay, it's a tobacco tar. And this is just we see relationships there. And then in blue we have the ambient exposures, where even at ambient exposures that we think of as safe, people have, of course, in the last 25 years or so, observed increased rates of cardiovascular disease related to those exposures. And you're going to hear a lot more about this. But he pointed out that we have this gap between these to look at. And some of us said, well, we believe that in that gap is where occupational exposures happen. And Kirk pointed out that's where cook stove exposures happen too. So we've done some work there. And I'm going to talk a little bit about some of that work in the aluminum industry. And we know from environmental studies that particulate matter is associated with cardiovascular disease, but that hasn't been studied in occupational settings. Partly, heart attacks are seen as being part of normal life, and we don't think of those as being environmental or occupationally caused. That's a relatively new way to look at things. So in this particular, so that has not been a focus of people in the occupational world until fairly recently. So basically what we were able to do is to collaborate with a major manufacturer, and they had a great deal of information that stretched back several decades. At facilities around the world, we focused on 12 major facilities, and within those facilities we had 55,000 total particulate. There was no size selection that was done for these samples. They were mostly collected for further analysis for, say, metals, for silica, for PAHs, for other materials. But the question was, could we take those and determine what portion of those were PM2.5 instead of total particulate matter? In this industry, we have smelters that are the big heavy duty work, and then we have the fabrication. It's also heavy duty, but they're making the aluminum materials that you know, whether they're airplane wings or they're the Coke cans. You know, they can be the whole range of aluminum materials. And we could see we could look at the total particulate matter and see that in the smelters there was a very wide range. Now, I just want to give you a sense of perspective. The US EPA says the 24-hour maximum should be 35 micrograms per cubic meter, or 0.035 milligrams. These are in milligrams over here. All right, so we are talking about really high concentrations in comparison. So the smelters have a much higher distribution and range of concentrations than the fabrication facilities and the refineries where these are first picked up. So the question again, our first goal in doing this, and you're going to hear more about these studies later, was to develop a way to estimate the PM 2.5 based on those data, on the existing measurements. So to do that, we conducted a sampling campaign where we actually had workers wear side by side both the traditional sampling cassette that does the quote total, that was the basis in this database with 55,000 samples reported by jobs and other information. And then we were using a newer method that would distinguish PM10 and PM 2.5 micron particles, with which we intended to make that distinction. And we collected almost 400 pairs of samples, personal samples, at 8 facilities to try to develop that relationship. And what we saw was, in fact, that we can look now at the PM 2.5 distribution and see that the smelter levels come down, and as do the fabrication. And actually, to put these together, this is the total particulate matter, and this is the fabrication of this total particulate matter, smelter and fabrication, and then this is the PM 2.5 smelter and fabrication. And as you can see, they have come closer together. And this will be important in a talk you'll hear later today in terms of where there seem to be some, surprises. You would expect we might see higher rates of heart disease here than here, and perhaps we do, perhaps we don't, or maybe not as much. But recall what I said about smokers too, that it's not as steep a slope as you might expect. So returning to the question that was raised, we have this gap in our data, and now having made these measurements in this industry, and now developing some exposure assessment, this is the distribution that we can now see among our workers, from the fabrication refineries to the smelter, in the aluminum industry. And you will hear later today, stay tuned, more about what the results of that study are. Okay? Now, in doing that, I was curious about, what can we know about submicron particles, which are also important? And we don't have a lot of easy ways we can't do personal sampling, particularly when we did this in 2010. But we decided to do a little bit of work on this, and so I should give credit, Dr. Elizabeth Noth did a lot of the work on the PM 2.5 total particulate. Now Dr. Saul Yu did some of this work on looking at the submicron and quasi-ultrafine particles. And for this work, we did area samples where we included the conventional cassette for quote total particles, and the new device that the people were wearing with the PM10 and PM 2.5. But also, we added a mini Moody, which is a cascade impactor with 6 stages. So it collects particles, cascading down, of different sizes. So we can define as under 1 micron, the particles under 1 micron, and also in some of the literature you'll see this less than 0.56, which is as low as you can go with conventional atmospheric pressure cascade impactors, as quasi-ultrafine. True ultrafine is 0.1, but at least we're getting in that vicinity. okay? So we had 68 sets of triplets. In order to make sure we've got good information, we actually had triplicates of each of those devices at each place. And we set them up at 34 locations at 8 facilities, most of those locations at 2 different days. And this just gives you some pictures of some of the kinds of facilities that we're looking at. This is intensive manufacturing. Okay. So this is looking at now each of the stages on the mini Moody. This is the smallest stage, and then the next stage all the way up to greater than 10 micrometers in diameter. So this would be your PM 2.5. Around here and down below is your close, this is the PM 3.2, close to 2.5. This would be your sub-micrometer, and this is your quasi-ultrafine. So what we see in the hot mill is that most of the mass is actually here in this quasi-ultrafine, very, very fine particles. All right, and then we see an increasing mass down here. But this is most of the mass is right there. And so we have that, and we can look at here, this is the greater than, that's a small thing. So keep your eye on these 2 areas. As I next move to the anode, another part of the smelter, and here you see very little in this quasi-ultrafine area, and most of the mass is greater than 10 microns in diameter. A very different distribution of the particle size. And we could present this together like this, and again say that here we have our quasi-ultrafine, which is compared over here. So they're really quite a difference, even though the anode has a much higher overall concentration of particles. The concentration that's ultrafine or quasi-ultrafine is much higher in the hot mill. So it depends on what's biologically important. And if there's one message I'd like you to get out of this, is that you need to think about the biology and what's important as you think about what is the particle size you want to focus on. And that's going to be quite critical. So here, this just looks at the total particle concentration, and what you see again is that in the hot mill is much less. It's maybe a third of what you've got in the anode for total particles, and that's the data that existed when we started this study. So one would say, oh, the particle concentration is much higher in the anode than in the hot mill, and that's definitely true. But if what was biologically important were the quasi-ultrafine particles, we see a very different story. It's actually higher in the hot mill than the anode, right? So I think I'm going to skip several of these slides. And there are several examples we can run through on this, looking at these relationships. This is, again, what we're seeing is we're going to see as we go through the various different parts of aluminum manufacturing, we see quite different particle size distributions, and within each facility we see different ones. So we can look at, say at facility A, this is the mass median diameter, and these are quite different. All right, so it's where the and this is the total particulate concentrations. So again, we're seeing up here very high particle concentrations, but the mass median diameter is high. And down here, this might be more important, even though the levels are lower. So we need to look more carefully at this, and this is some of the work that we're trying to do now. And looking at, so it's an interesting world to get into. Again, there's just developing ways in which to do personal sampling for ultrafines. By the way, these mini cascade impactors are several $1,000s a piece, so they're not easy, to get 60 of them to do a research study. which is what we had for the others. As you can see, we collected samples from a variety of locations, and this is the refinery distribution. Again, not surprising, in the refinery most of the particles are on the large size as opposed to the small size. Welding, on the other hand, is something where welding fumes are very small, and so people who were doing welding, we found very high concentrations in the quasi-ultrafine range, and then, of course, in the submicron compared to the others. So, again, just these, you see very different pictures in looking at the different processes and what's going on. Again, I'm going to kind of quickly go through these slides, looking at the time, and just say, okay, let's see. So, looking at, again, going back and looking just at the mini Moody samplers that we have, this is the distribution of the total concentrations we observed in the smelter compared to in the fabrication room. Clearly much higher here than here. But if we move to the submicron particles, we see that that difference is reduced. We've reduced that difference in those two things, and by the time we move to the quasi-ultrafine, there is much less difference. If anything, they may be somewhat comparable. So if what the active agent are ultrafine particles, the smelter, clearly you walk in, it's dirtier, it looks much dirtier, it feels much dirtier, and it is dirtier in terms of total mass. But in terms of what's going to make it to the biologic target, that might be quite different. So these are things that we need to be bearing in mind. And so looking at those data, we want to say that the total particle concentration was significantly higher in the smelters than the fab, but the submicron and quasi-ultrafine particle concentrations were similar in there. And so we really need to do further investigation into the ultrafine. I will quickly, I'm just going to very quickly say, all of this can change even further if we look at respirator usage. Because where the concentrations are highest, then we might be using respirators. So this is an ongoing study that we're working on now, and you can see the evolution over time. Black dots are samples that were collected without respirators being used by the individual, and red when they were being used, and clearly there were changes in the policy of the company. And so that's clearly going to change the actual dose people get. So that's among the stuff that we're actually working on. So I think I will stop there and say, you're going to hear a lot today. There are a lot of wonderful speakers. I'm really honored to be on the program with these other speakers. And so you'll hear a lot more in depth about several of the issues that I've just touched on. But I think the big thing I want to say is that I haven't even talked about composition. I'm a chemist, right? I think composition is really important, but I think the focus of this is in general particles, and we can see, I'm trying to help you focus on particle size, how at many dimensions that can be important, and the concentrations may change drastically. Combustion products, if you can remember this, tend to be in the ultrafine stage, although they coalesce, so some distance away or over time, they coalesce to larger particles. So that will change. So that's a more dynamic kind of thing. And at that, I think I will stop.
Thank you, Kathy, for that great introduction to our topic. Barbara, do you have a question?
Yeah, are you wanting
Yes.
full questions? Or?
No, we can have a couple
I
questions.
just was interested, very interesting talk around how ultrafine particles respond in the presence of oil mist. I mean, do they,
Okay.
is oil mist protect, I'm assuming there's oil mist in the fabrication and not in the smelter? But I'm not sure.
In some places, yes, not everywhere, but yes, in some places. So, in general, this is not specific to any particular setting, but just in general, theoretically in the aerosol technology world. the way you get the fastest and most efficient aggregation of particles and a drop in the ultrafine particles is to have a lot of ultrafine particles and a lot of big particles, a mixture. It can make it 10 times faster, the rate at which it coalesces and aggregates. So if you have a mixture, whether it's oil mist or anything else, any other particle, that mixture is going to lead to the ultrafines dropping off pretty quickly. So now, what we observed actually, we would have to go and say how close are we to the source, because it's dynamic. As you move away from the source, you're going to see less of the ultrafine because they're going to coagulate. So in the presence of oil mist, yes, you would see less ultrafine than if you had just the ultrafine by itself. Does that?
Yeah, no, I'm just trying to figure out, because is it a protective factor, oil mist, in a way? Although, interventions aimed at reducing oil mist would obviously also.
No, I would not go that direction. I mean, it's a little bit like you could spray, an inert particles in the air and have the same protective effect if you're going to do that.
Okay, good.
I think Drew, Jennifer, and this gentleman here.
Yeah, great.
Yeah, Drew, I think.
Yeah, thanks, Kathy. This is a great talk. I think maybe you skipped over some of this. I'm curious, in a world where arithmetic mean defines, PM2.5 concentrations, regulations, epidemiological dose response literature, but where the actual distribution of particles, is log linear more or less. What should we, as budding researchers and practitioners, be thinking about as a way of, how to actually report central tendencies of these particles? Should we be looking at geometric means, and if so, how do you even relate that back to the epidemiological literature, which is on arithmetic means?
Okay, so let me answer that a little fully. This is a really good question, an insightful question. You're absolutely right that distributions of these samples tend to be log normally distributed, which means the appropriate descriptor of the central tendency is the geometric mean and geometric standard deviation. And I believe those should be reported. However, the actual dose that people get is actually related to the arithmetic mean, not the geometric mean. So, because if you think about it, when you have that tail out there, that's the high concentration, people will periodically get that high concentration, and that's what's going to go into their average dose. So, in the epidemiologic analyses, one should use the arithmetic mean. I believe, and I fight this battle, even in my own groups, that we should report both arithmetic and geometric means and standard deviations, because they have different meanings and they have different usefulnesses. If you're going to predict someone's exposure the next day, you'd want to have the geometric mean. But if you want to know their exposure over a year, their cumulative exposure, you want the arithmetic mean. Okay?
Jennifer, is your question quick?
Yes.
Oh, there you go.
If you go over the study period, have there been any changes in processes used, and do you anticipate that would change what you see?
Absolutely, that's actually a whole set of slides I took out. So Betsy Noth has been doing a lot of work looking at the changes in processes, some of which are for the purposes of efficiency and some are for the purposes of controlling exposures, and looking at some of those changes. So yes, that does enter the picture as well. So one does need to look at time trends as well.
Sir?
Do we know the transfer mechanism of the ultrafines into neurons and eventually into the brain?
It's an observation in animals that they observe that if they exposed rodents to ultrafine particles, they could see that they seem to go from the nasal passage directly into the brain. And the assumption is they're following the nerves through there. And I don't know, John is going to be talking more about the mechanisms in general, about that part, okay. But anyhow, this translocation is considered to be very important, but we don't know much about it. It's kind of an area of research, really.
Thanks again, Kathy.